Good morning and once again welcome to my YouTube channel, Pearson and Excel International Maths by Mr. Kamoto. And today I want to introduce a very important topic to you. This is topic number 3, chapter 3 of P2, and we are looking at 2 and binomial expansion. This is a critical topic because we shall be having another binomial expansion in pure mathematics 4, and therefore I want to use it only. Binomial expansion means expanding a function or expanding a statement whereby we can start by talking about a plus b raised to power 0. Obviously this is 1. Anything that is raised to power 0 is 1. But we can have a plus b raised to power 1. It repeats itself. This is a plus b. But I would want us to look clearly and closely at a plus b squared, which to me is a plus b multiplied by a plus b, which ends up being a squared plus ab, a squared plus ab plus another ab plus ab plus b squared. If you collect the like terms here, you're going to have a squared plus 2ab plus b squared. And that is an expansion. But if you look at a plus b now cubed, it becomes a plus b multiplied by a plus b multiplied by another a plus b, which basically means this one, because it is expanded twice, a squared plus 2ab plus b squared multiplied by the third time a plus b. And of course it goes without saying that a squared times a is a cubed, a squared times b is a squared b, and 2ab times a plus 3a squared b, or rather 2. This is 2. You see, I'm already making some errors, and this explains where I'm heading. 2ab times a is 2a squared b, and 2ab times b plus 2ab squared, b squared times a plus b squared a plus b cubed. If you collect the like terms, a cubed will stand alone, a cubed. A squared b plus 2a squared b plus 3a squared b, 2ab squared plus b squared plus is equals to plus 3b squared a, because of that and that, of course, plus b cubed. You can see the amount of time and the amount of space I'm spending expanding these expressions. But one thing I want us to look at this so that we learn how to save time when we start using what we're calling the Pascal's triangle. And I want to look at what is happening here and say, there is, when we are starting with a plus b cubed, the first term is a cubed. The second term is 3a squared b. And I want us to study the behavior of the indices. The first term has the highest index in the first term, that is a cubed. When we get down, A reduces its index and B start coming up. In this particular term, B was having index of 0. Here, A is going to have an index of 2, B the index of 1. Silently, there is a 1 there. And you can see A is having an index of 1 and B now the index of 2, and that is the third term. In the fourth term, A is having the index of 0 and B the index of 3, which is the maximum index. So indices, index behavior. Indices, let's talk about indices behavior. Term 1 starts with the highest index, reducing by 1 till index 0. That is one thing you have to note. And term 2, this is term 1 rather, term 2, and when I'm talking about term 2, I'm talking about this. This is term 1. Term 2 starts with index 0 increasing by 1 till the highest index. And with that, I will explain that with this. If you look at this expansion, A plus B cubed, the highest power is 3. So A enjoys the highest term in the first term. It keeps now reducing by 1 until it will be having the index 0. So 3, 2, 1, 0. What about B? B starts with 0, 1, 2, 3. Incidentally, you must note that in every term, the total indices is 3. So this is 3 plus B. There's a B raised to power 0 there silently. So 3 plus 0 is 3. 2 plus 1 is 3. There is a 1 here. 2 plus 1 is 3. And there is 0 there. 3 plus 0 is 3. It will all 3 because it was originally the index. Now, before this, I would also now want to introduce how then do we get this coefficient 3? Where is the 3 coming from? And where is 3 coming from? There is a 1 there. There's a 1 there. Where are those coefficients coming from? You will agree with me that this method, expanding a term like A plus B raised to power 4 is going to take us a lot of time, and we are likely to make mistakes. So we know very well that the highest power, A starts with the highest power. So we are going to have A power 4 plus A power 3, B power 1, plus A power 2, B power 2, plus A power 1, B power 3, plus A power 0, B power 4. We are sure that we are going to have that kind of expansion, but where do the coefficients come from? These coefficients now, 1, 3, 3, 1, will come from a very, very interesting introduction here. So, and that's for now what we call the Pascal's triangle. The Pascal's triangle gives the coefficient of the binomial expansion. And fine, the moment we raise to power 0, the moment we raise anything to power 0, power 0. Of course, the whole term becomes 1, even as you can see here, the whole term becomes 1. The whole term becomes 1, so the coefficient is 1. The moment you raise to power 1, you can see the coefficient. We are talking about the same term, and the coefficient is 1, 1. When anything is raised to power 1, then it becomes itself 1, 1. The coefficients of term 1 and the coefficients of term 2, there is 1, 1. But what about when we raise it to power 2? When we raise it to power 2, we have the coefficient here, as you can see, power 2, 1, 2, 1, the coefficient. How does the Pascal's triangle ensure that those are the coefficients? We always start with 1. When we add 1 plus 1, we get 2, and we always end with 1. What about power 3? We start with 1, we add 1 plus 2, 3, we add 2 plus 1, 3, we keep adding to give us the next. So, and of course we end with 1. And sure enough, the coefficient when we are using power 3 is 1, 3, 3, 1. So we can already confirm with this here. Power 3, this one, which is here, 1, 3, 3, 1. So power 4. So when we are raising any expression to power 4, we start with 1, 1 plus 3, 4, 3 plus 3, 6, 3 plus 1, 3 plus 1, 4, and of course we end with 1. So therefore, the expression that we have come up with up there is going to be a to power 4, a plus b to power 4 is going to be a to power 4 plus a3b1 plus a2b2 plus a1b3 plus b plus b3. Now we bring in the coefficients. We have 1, we have 4, we have 6, and then we have 4, and we have 1. So that becomes the expansion of a plus b raised to power 4. Look how much time it has saved you, how much space it has saved you, and you are not likely to make mistakes as opposed to every other method. I don't know how much time it would have taken me to expand a plus b power 4, which would have been a plus b, a plus b, a plus b, a plus b. This is now what I call the donkey work, which to me, it doesn't work. So the binomial expansion comes in handy to assist me when I want now to expand large expressions. And that is just an introduction. Remember, we have learned two things. One, the power, the index. Term 1 starts with the highest index, reducing by 1 till index 0. Term 2 starts with index 0, increasing by 1 till the highest index. Please remember that. And of course, don't forget about the coefficients, which are brought in by Pascal's triangle. So even if you are supposed to expand by power 5, it will still be 1, 1 plus 4, 5, 4 plus 4, 4 plus 6, 10, 6 plus 4, 10, 4 plus 1, 5, and of course we end with 1. It's just how easily we have obtained that one. So be on the lookout even as I introduce the very first example in this. All right.